Attention.
Well, thank you everybody for joining me this afternoon or evening or tomorrow morning for Henry over in Germany. Um, we're going to have go through about 36 slides, and the focus is mostly on pasteurization, but we're really addressing the prevention of re-fermentation in the package and assuring stability of our packaged beverages. Um, and so it's funny how brewing has changed in the past 10 years. We sort of saw it with the barrel-aged beers coming out in wild brews. Whoever knew that breweries would be making all kinds of other products as they are now? New product development, NPD, is so important into what our companies are doing. And that was kind of what brought me to say, hey, it's time to remind people of what we know and where things are going. And I do apologize. I have dogs in the room with me, and they're beginning to yawn and act up a little bit. So, but let me move along. My talk today is going to start off with a discussion of microbiology. And then we're going to go to some cold stability options, sterilizing options, batch pasteurization, flash pasteurization, and we'll close up with a discussion on tunnel pasteurization. And a couple of things. We're going to walk through some calculations that were really established in the late 50s. We're not going to really do comparisons of technologies today. We are going to discuss sterile filtration, flash pasteurization, and tunnel pasteurization, but we're not going to go through which one uses more energy, less energy, CapEx, OpEx. That's for another time or another place. This is certainly not a survey of solution providers in what I'm doing, but I will be showing a few pieces of equipment by a couple of American vendors. For example, we have Henry. Henry works for KHS. KHS make very fine flash pasteurizers. Unfortunately, as well as tunnel pasteurizers, and neither of his technologies are shared in my presentation today. But anyway, we'll get into this in, I believe, a pretty reasonable engineering perspective. Well, the thing about this is a paper that came out last month from one of the ACS journals, a really lovely paper that explores, the old standby thing that we think that every year a dog ages is 7 years. Sadly, the conclusion through the process they used was the first year of a dog's life is equivalent to about 18 years of a human's life, and then it slows down. But I like the graphic from the article. Honestly, the article is above my head, but we have to grow and maximize what we're doing in our breweries to stay alive and to survive. And we have to basically grow a dog year. So hopefully some of the things I'm sharing will be interesting. Well, what are the unwelcome microorganisms we deal with in brewing? Well, we have Lactobacillus spp, we have Pediococcus damnosus, we have Saccharomyces type yeast, the wild yeast strains such as Diastaticus, Serratia, maricens, Acetobacter, Glucanobacter, Megasphaera, Pectinatus, Zymomonas, a little rarer, but if you've had any earthworks done, you've probably brought in Zymomonas on your boots. Various spores, Pseudomonas, not that often seen, but it causes ropiness and other things. If you're working with fruit juices, you're possibly introducing Bacillus coagulans, some molds, and a few things. And of course, with beer, you're bringing in, if you're making certain kinds of beers, Brettanomyces bruxellensis. And the interesting thing about the options we have is you kind of need a microbiological lab to kind of figure out how good you're doing. I just put up a picture of some of the disposable, fairly inexpensive media that takes several days to get a reading on. We'll talk a little bit about PCR technology. PCRs are growing and they're getting more robust. The false positives are being handled pretty well, I think, by the manufacturers. But traditional aerobic plating is really the gold standard. Some people would say with anaerobic too, and we'll talk about that just briefly. But so now we're going into a little bit deeper into the microbiology. The accepted aerobic plate count ranges that you find in the literature for breakfast cereals is 0 to 100 plate counts, cell-forming units per gram. You go down to frozen vegetables, it's 1,000 to 100,000. Go down to walnuts, it's the Wild Wild West. It's 31,000 to 2 million. Raw milk, 800 to 630,000. Pasteurized milk is a lot lower, 100 to 75,000. When we look at herbs and spices, we see the protocols are a little different. This is the European microbiological criteria, where you take 5 samples and you elutriate them in water, the 25-gram samples, and you filter them down. And for example, if you look at Clostridium perfringens, 1 sample out of 5 can have between 100 to 1,000. So you kind of get a feeling that the numbers aren't 0, the numbers aren't 1. So what does that take us to? Well, if we go to the aerobic plate count standard pour plate method, and there's a citation for it, and you can look it up. There's plenty of things on links to it. There's an official plate count agar, the BAM Media M124, and there's links to that. But we in brewing have specific media that we're really happy with. Racaray, Sue, Lin, NBB, UBA, Universal Beer Agar, which is made with beer. And that's a particularly good one for a whole host of different things that grow in our beers. And when you plate it up and grow it in an anaerobic environment, you get different information. So sometimes it's good to have plates that you have an anaerobic space. So what are the kinds of numbers we're looking at? Well, obviously, what is desired is a non-detectable or less than 1 CFU per milliliter. In a lot of places, a lot of independent labs, like the ones I use, they're reporting CFU per gram. But because basically the density of beer is 1.006, 1.009 grams per milliliter, they're pretty much the same. So we're looking for less than 1 for aerobic bacterial testing, anaerobic bacterial testing for yeast and mold. However, what's commercially acceptable is typically less than 80. That's the magic number. Now, for me, when I get to 30, that's when I start retesting and getting concerned. But there's perfectly soft in the other foodstuffs that there's numbers are allowable, although we always strive for a less than 1. You know, when we talk about milk, we have a short shelf life. So that's how milk can have so much more than beer. We'll talk maybe a little bit more about that. Okay, so let me go into the first options we have. Back 100 years ago, it was known that bisulfite and metabisulfite were served as preservatives. They also serve to arrest fermentation. So if you want a sweet product, you can put those in. And then we jump into the late 50s and 60s. Diethyl Pyrocarbonate was a chemical sterilant that you added. Heptyl parahydroxybenzoate, that came on board about 1963. And then we had several others. There's one product there called Velcorin, developed in Germany, dimethyl dicarbonate. Germany was the first country to actually allow it, not in beer, but in everything else that's carbonated, in wines, in their ciders. I know several cideries in America that use it quite effectively at clean counts. It's cold sterilization. And of course, there's benzoates, the class E211 classes of inorganic chemicals, sorbates, and work continues to go on. The most recent preservative I've seen that is really a sledgehammer against all kinds of microorganisms is Nagardo. Lanches, which is one of those German, Chinese, Swiss conglomerates who created Velcorin, have this product, and it's a natural product. and it means, it's a funny name. Nagardo means natural guardian, and it's it comes from French Guiana, from particular fungi and the glycolipids that they make it a powder, and it is natural powder. It's 50 times more effective than anything I put in that previous page. Um, and so, and it's been approved by the FDA. Now, I don't like using preservatives myself, uh, but they're part of the toolkit for some beverages. But as brewers, we kind of like having more natural options, more natural even than something like this. So let me move on. And, I'm just going to talk about one sterile filtration, commercially sterile filtration manufacturer, but let's not forget the Sartorius, Millipore, and several others have their versions. I am kind of impressed by the Paul CFS Neo. Um, and I'm going to try to eliminate, I'm getting annoyed because I'm seeing all these pictures, other pictures there. And I couldn't see my presentation. They have this system with a kind of cocky. It's called the Paraset, which is designed for pasteurizer replacement in beer. And it consists of pre-filters and hydrophilic membrane filters. Now, when I started up in brewing in 1983, sterile filtration, commercially sterile filtration, meant a 4.45 micron filter on beer, but it had to be really clear beer that you're presenting. Uh, 20 years prior to that, the number was 0.8 microns was considered as sterile filtration. But the reason that was that is that was the case is commercial filters weren't very good. They were smaller than 0.8 microns. So then it moved to 0.45. And now the new way of discussing the performance is really species specific. You challenge, you get a beer or you get a water and you put in a certain loading and you actually measure what comes through and you look at the reductions on that. The interesting thing about this technology, though, the way they make these membranes, is now the membranes require CIP after 45 hours of continuous operation. And as you can see, they come in groups of 7. So although they run in parallel, you can isolate them, go through cleaning. And Paul has worked with, I believe it was Ecolab, might be somebody else, for enzymatic cleaners. So they recover like 99.92% of the flux, the liters per meter squared per hour through them after each wash. So they last a long time. So membranes, to give them credit, are a lot more cost effective, have a lot greater throughput, and higher flow rates. You can do 400 hectoliters an hour easily through a set like this. But again, you need really good pre-filtration, but that's part of it. Okay, beer and beverages. Now, we know that beer has natural components within it that serve to challenge unwanted microorganisms, hops, alcohol, reduced pH due to carbon dioxide. I mean, we know that because there's so many small breweries making great products that last a long time that have no kinds of interdiction. They don't use chemical treatment, preservatives. They don't use sterile filtration. They certainly don't use pasteurization. And yet, and they're doing this. But we're going to change the talk in a moment to pasteurization. The first federal standard for milk pasteurization was at 61.7 degrees for 30 minutes hold of the glass bottles. And that was because they were worried about tuberculosis, Mycobacterium tuberculosis. And that was in 1924. But then Clostridium burnetii was recognized as heat resistance in 56. So with a little work, the FDA, USDA came up with a new regulation which passed 63 degrees for milk as the minimum. And just remember, thermal systems, where we're going to right now in the discussion, inactivate cells, whereas membrane filtration works by removing cells. And there's an implication there with PCR. Just remember, if you have membrane filtration, you don't have to worry so much about getting false positives when you amplify and do the enzyme extraction and the buildup and then get the signal, because you don't have any fragments, you've removed them. But if you thermally inactivated, you don't know that. You don't know that. All you do is get something in it. You're magnified. So it's something to keep in mind with if you're working with PCR. As I've said, PCRs, I was never a fan of them for the first few years. I am now, but because they were a little too specific. You could have an infected beer, but because you had such specific targets, if it wasn't one or two targets, you had no idea that you had something else. But now they're much broader, and you can actually do a bank of tests. PCR has really been amazing, and it's better than nothing. So, okay, so let's go talking about what's happening with heat. Here's a picture from a fun physics book for kids, where we have, in this case, we have a robber. We want to stop him in his tracks, and they're playing around with potential energy and kinetic energy. Well, I'm using something else. I'm dealing with thermal energy, and that robber going through there, that raider, is it could either be bulk beer through a flash pasteurizer, or beer in a can, or beer in a bottle. And instead of kinetic energy, we're really going to do the work we do by increasing chemical potential, the kinetic energy. We're going to kill things and denature enzymes and kill microorganisms because of the heat that we're applying. Now, the story of pasteurization goes way before Louis Pasteur. Applying heat to preserve and extend product life has been documented at least since 1117 AD in China, written documentation. And it shows up at a bunch of interesting times before Pasteur formalized it. Now, Pasteur was looking at beer, wine, and milk at different times, but all in the same thing. And in 1864, it's when he really focused on wine first. He was paid for it by the French authorities, the government, because they wanted to stabilize and make their wine travel longer and be more robust. So he heated it to 50 to 60 degrees centigrade, which is up to 140 degrees Fahrenheit, prior to aging, to kill microbes and reduce acidity that would happen because of microbial infection. And he also worked on beer. So now we have a formal definition. The Codex Alimentarius Commission of the World Health Organization and the Food and Agricultural Organization of the UN defined terms commercial sterility for low acid food, which we have with beer, as the absence of sufficient microorganisms capable of growing within it at normal non-refrigerated conditions. So basically, we want to knock whatever's in our package, whatever is in our beer down so much that it's not a threat. Now, in 1905, first of all, when Pasteur did his work, almost immediately, brewers in France and Germany, and then, on the continent, started pasteurizing beer. And here's the description, and this is found, I forgot who the author, but it was published in 1905. Ian Hornsby, in his wonderful 700-page book, The History of Brewing, which he was commissioned by the Royal Society of Chemistry in the UK to write, has this quote: "The lager beers of this country, that is beer brewed on the continental system, are pasteurized or steamed in bottle. The filled bottles are packed in cases, placed in a tank of water, the temperature of which is slowly raised to 140 degrees and maintained for at least an hour. The water is then gradually cooled. The object of heating is to kill any yeast cells or organisms and to prevent any further fermentation. Pasteurization imparts a somewhat cooked flavor to the beer." But he held it for an hour at 140 degrees, and there was a slow heat up, because it was heated, I believe, by direct fire or by hot oil recirculating through a pipe through a tube, and then he cooled it down. It took a long time, and we'll talk about the calculations of what that was. an interesting thing that you can still pasteurize beer. I never recommend it in a batch pasteurizer by placing it in water. You have to make sure you're going to end up probably over pasteurizing it because you're going to put a bunch of bottles on a stovepipe or in a heater. I've used an IDD Mini King. The chemical detergent set is perfect. You clean it out, put it in water. It has a nice electrical heater, and you can stick 2 cases of beer in it and stick several thermometers in some of the beers to make sure you get up, hold it. It holds it really nicely. So if you have an IDD Mini King, you can mess around. But the trouble is when you're using water, you can't really assure, you don't have good circulation. You can't really assure that you're getting uniform pasteurization. You will get some over pasteurizations. That's why batch pasteurizers that are any good use water sprays. So these are some batch pasteurizers from a company. I'll talk about the company a little bit my next slide, a Wisconsin company. So it seems appropriate for MBA District Milwaukee that I'm using Pro. Pro are not the only ones with batch pasteurizers, but they have different models. One model has 1 temperature. The other model has 3 temperature set points. A unit like this, you basically load beer on a tray and pull down the cover, and a hot water spray, water at a certain temperature is recirculated, and you can keep track of the temperature and give it a certain heat soak that you want. And you can process on an 8-hour shift 3,000 bottles. You can process a little more cans because cans have a faster heat transfer through the metal, but yeah, a couple of cases of finished goods in an 8-hour shift. So it's a kind of a fun technology in the sense that if you've got all kinds of great products, say you've never needed pasteurization, but now you're in a whole new realm of products that might be fruit inclusive. For example, there's a beverage, a Spindrift, that I enjoy. It's made with 5% fruit juice. Well, that's actually made at City Brewery in Latrobe because they have a pasteurizer. So, and there's no preservatives in it. It's just natural, pasteurized product. So with a batch pasteurizer, you can kind of play around and then decide afterwards if you have a winner, if you want to go to the next level of pasteurization. So let's stop for a second and talk about some calculations. Not too much, but just to have a basic understanding. If beer is pasteurized at 60 degrees, the number of pasteurization units, PU, is equal to the length of time in minutes of heat treatment during pasteurization. So if beer is pasteurized at a temperature a little bit higher than 60 degrees, T degrees C above 60, for a time of T minutes, then the effect of pasteurization increases by a factor of, and here's my little factor. Note that that's subscripted. At the end of this presentation, I have a few references. So the reference to this comes, but this comes back from in the 50s. So there's this factor. Basically, the amount of pasteurization units, PUs per minute, is equal to 1.393 raised to a certain power. That power is the temperature you're pasteurizing at minus 60. So that means that we can calculate the pasteurization by a simple algebraic rearrangement. And let me show you an example of equation 1 applied. If we pasteurize for 10 minutes at 62 degrees centigrade, that's the bulk of the beer inside the can, the bulk of the beer inside the bottle, or the bulk of the beer inside a holding tube or a heat exchanger. Then we just go through the math, and applying equation 1, you see it calculates out to 19.4 pasteurization units. So back in 58, Basket published this nice little paper called Pasteurization Unit, a Tool for the Brewing Industry. And he defined 145 degrees back in 1958 for 1 minute, gave you 1 pasteurization unit. Today it's 140 degrees. But the kind of neat thing is about this, so if we were to raise the temperature to say 170 degrees and bounce it off the chart, now we're at 18. So as a brewer, you have a couple of choices. You can hold it at basically 145, according to this old plot. Hold it for 18 minutes, or you can raise it up to 170, hold it for 1 minute, and then chill it down. What we're trying to do, of course, is shooting ourselves in the foot or other places by having a pasteurizer that allows us to sleep well at night and not worry about fermentation happening in bottles, in cans, and sometimes in kegs. So we're not going to go through the calculations. Another way of describing the kill of pasteurization is through the Z factor. And the Z factor is 7 for microorganisms causing spoilage in beer. Superscript 2 shows that there's another reference at the end of my talk. Consider Z as the temperature change required to reduce bacteria by a factor of 10. Now, earlier I made a comment about milk. Well, with sensitive and shelf life challenged beverages, such as milk, we strive for a 5 log reduction in the number of microorganisms in the beverage after pasteurization, killing 99.999% of such organisms. We need greater reduction at beer. When you buy milk at the store, it's refrigerated, it's cold, and unless it's ultra high temperature, long life milk, it has a very defined shelf life. It's a lot less than any beer. So, well, I say that. There are some New England IPAs, ... But this log reduction value, just to show you the calculation of the likelihood of one specified microorganism, let's say it's, we're talking about a lactobacilli, that we can quantify through our aerobic plate count the number of viable organisms before treatment and after treatment. So we have the log reduction value is simply this equation. Another equation, I didn't put another number to it, it's just kind of background information of log base 10 of A minus log base 10 of B, the before and the after. It's a logarithmic relationship. We really want to get 10 to the 5 reduction. That's what we get from milk. That's from 100,000 to 1. However, that means if we had 100,000 in a milliliter, 100,000 of quantifiable microorganisms, we want it down to 1. However, for beer, we really want 10 to the 6 or higher. I mean, you can sleep even better if it's 10 to the 7th, and that is possible. Again, there's always compromise. With a pasteurizer, that means you're going to probably have to heat it up more, and then you worry about, how am I affecting the beer? If you ask questions later on, I can talk about some work that I did back in 1998 on hands-on work with a pretty major brewery on quantifying what happens to the flavor of beer when it comes out of a pasteurizer and over the next few weeks compared to a control. Okay, another way of characterizing that we don't use as brewers, but it's used in the space that's generally above pasteurization, but below retorting. Retorting is when you take something up and you're going to take it, the container, way above boiling. And technically, you should do that with coffee. Anybody making coffee is always taking a risk if they're not retorting, because that coffee bean has dropped on the ground. When it drops on the ground, it can come in contact with Clostridium botulism. Well, Clostridium botulism is going to survive the roasting of the bean, the transport of the bean, the grinding of the bean, the making of the thing. So it's just a mathematical thing. We all make business decisions, but if you try to buy cans for making coffee in a brewery, you'll probably be asked by the can supplier to sign a waiver, if they even agree to sell you the cans, if you're not going to satisfy them that you're retorting, which is taking up that packaged coffee to 230 degrees Fahrenheit for a certain time, because you have to kill the spores. That's the concern with anything that drops on the ground. So back to the time above temperature characterization. An alternative characterization, quantification, and pasteurization is this TAT, time above temperature, which is simply the amount of time which the temperature of the target is equal or higher than 60. So you have this funny differential equation, K, which is the time above temperature, is equal to bump everything in equation 2. Well, let me put a real calculation on it. Let's say we have a beverage and we take it up to 63 degrees for 5 minutes. Well, the results of that, when you do a simple algebraic manipulation of equation 2 and take what we call the integral of that, you get basically 5 minutes at 3 degrees above that target of 60 gave us 15 minutes of the time at temperature, time above temperature. So the reason why this is important is food scientists kind of like to say, I want to hold something at a certain temperature for a certain number of minutes. But if you exceed that, there's an equivalence that the time above temperature characterization allows you. If you ever get to really exotic fruits and vegetables, you sort of have to go higher temperatures and higher pasteurizations, but that's not the focus of this talk. Factors to consider when you're looking at flash versus tunnel pasteurization. The available footprint to install a pasteurizing solution. A tunnel pasteurizer is going to take a bigger footprint. A flash pasteurizer is typically 1/3 the footprint. And heck, if you talk to Henry and you buy a $2 million KHS filler, you might as well stick the flash pasteurizer, which is going to cost you another $500,000, on top of it. They actually sell them on stands. So the entire footprint is on the top. Henry can comment and share about that. The KHS is kind of funny because they seem to really put packaging lines in really tight spaces. So the space above the filler is fair game in some installs. The flexibility to change the target pasteurization for different temperatures, different beverages, is really important as you think about what's going on for the future. You never really want to just constrain, I want a pasteurizer that's going to give me 12 PUs or 18 PUs. You want to have ranges, and you also want to have different kinds of packages. The pasteurizer I put in for 100 bottles per minute at Susquehanna Brewing Company, it was 35 feet long, 5.5 feet wide, 6 feet working volume. And that could accommodate 22-ounce bottles. That could accommodate 12-ounce bottles, accommodate cans. But you have to make sure you specify. The energy and water consumption parameters are very different between flash and tunnel. And they are also with sterile filtration. Same as the operating expenditures and the capital expenditures. Again, this is not the place. And if you ever really want to consider them, I do have, if you go to my pages at academia.edu, I have a thing on engineering economics, and I have a case study there of using life cycle cost analysis. Just look up life cycle cost analysis, how to do it on the internet. Sometimes the things you get through Google are actually correct. And there's great examples that you can do like to like and compare. And care and feeding preventative maintenance. For the hazard plan, you probably have to put in place what your manufacturer says. For example, your flash pasteurizer, you've got a heat exchanger. Well, you've got to inspect every couple of years, depending on the heat exchanger, the gaskets. You've got to replace them, have the gaskets ready. There's certain things with tunnel pasteurizer, you have to take off panels, just make sure the spray heads are not blocked. There's certain things you have to do, and they're different. So let's talk about flash pasteurization. And right now I'm talking about the ones that have a characteristic that's unique Jeff Gunn design. IDD are manufactured in California, family-owned company. You see them in a lot of places. Many of us have worked with them. And the characteristic thing is their holding tube is a circular spiral, a nice way of reducing the footprint, putting it on a skid. And I believe the heat exchanger, I can't see in that one, but I think he sent me the pictures, but I think that's a Thermaline, which is American manufactured. But basically you've got two tanks. The big tank is for CIP. The small tank is for the sterile beer, the heated beer tank. I won't take you through a drawing, but ask me questions. But basically, we bring in cold beer. We're going to heat the beer up. We're going to take it to a holding temperature, and we're going to hold it for a specified amount of time, and then we're going to cool it down. And by using a plate and frame heat exchanger, I think Jeff can get 96% heat recovery, heat exchange. It might be 95%. I think he claims 96. I think you have to check with the actual heat exchanger. It might be 1 degree plus or minus different, but that's the that's the tunnel pasteurizer. I mean, that's a flash pasteurizer. Flash pasteurizer has an important component is the pump that feeds it. There's different ways of doing this. A steady state approach where it's a steady flow, and near the end of the tank, it could be a variable speed flow. Again, I'm only talking one manufacturer, but IDD have several options for you and several proven things. Now, the reason why flash pasteurizers are so important is those of us who are concerned about kegs realize that when you put beer in kegs, that a keg is just a little break beer tank. And hopefully that keg has been transported cold, put in a cold room next to the bottles, next to other kegs and unpasteurized products. The distributor goes to the bar and is kept refrigerated. Imagine if you put a bright beer tank and put it out in the sun. Well, the nice thing about flash pasteurizing beer is that takes what you can really sleep well at night. And again, ask me questions if you want to talk about how what flavor changes may be perceived. It's not what you think. This is another formerly made in the USA. This is no longer made a flash pasteurizing company. But here you see the holding tubes are on the top. There they have a different heat exchanger, SPX. Some things about heat exchangers and flash pasteurizers is they do require more complex filler enclosures. The surrounding around whether you're canning and seaming or bottling and crowning. You need more rigorous microcontrol and you have greater risk of contamination. That is because the beer leaving the flash pasteurizer hopefully goes to a sterile beer holding tank, but then moves onward. As soon as it leaves the skid, you got to be really careful because you can reinfect. And here's how Jeff counsels it. And by the way, so what happens? Well, here's, for example, cans going off a depalletizer. Great one made by Scott Fab. The Can-I bus, cute being from Colorado system. But you have cans, and they've got to really be really well rinsed, either air rinsed with ionized air, so they pull off any dirt, or water rinsed. And that water rinse should be sterile water, and it could be water with a little bit of a sterilant in it. You got to be careful and use something. And I'm trying not to name brands, but I can't help it because Jeff gave me a quote, and I'm going to use it in a second. But there's a greater risk of contamination that you have to manage, and you have to document it in your food safety plan. Here's my cans as seen through the Perspex, the acrylic filler. This is a Crohn's volumetric can filler making my product. It's an enclosed environment. Well, if I was going through a flash pasteurizer, I would need on top of the filler and on top of the seamer, a sterile air hood that brought in sterile air, made it sterile by sterile filtration and or UV and positive pressure. And there's some other belt and braces approaches. Now, here's another one of the linear fillers we see. Linear fillers are really a challenge microbiologically because you have to basically build your own enclosed enclosed cover if you're going to hope to have a near aseptic filling environment. Now, one of the interesting things that I have, let me go to Jeff's quote first of all. Flash pasteurization and aseptic filling and crowning or seaming. Jeff said, I generally use Oxine, that's the brand name, which he represents, in full aseptic systems as an addition to ULPA or HEPA filters at 20 to 50 ppm. 20 to 50 refers to the oxine strength. The fogging of oxine breaks the CO2, chlorine dioxide gas out of solution, so you create a microclimate of CO2 gas, challenging surfaces around the filler heads, fill tubes, seamers, cans, and lids. The seamers consistently indicate that the highest microlobes during operation, so it's important to fog even when the line is at rest during stoppages and breaks. Oxine works extremely well, 20 parts per million with filtered air, and great at 50 ppm without filtered air, so long as there is an enclosure to maintain the microenvironment. Now, my first time of ever seeing this was at a Pabst brewery that had a 100-year-old filler. I mean, it was like mild steel, painted over. It was massive. It had like 72 heads on it. But they sprayed peracetic acid solution in atomizers all over the place. If you breathed it, you'd scorch your nostrils and your lungs. But that's how they made their draft beer. And it was microbiologically clean. They just kept the entire room misted, but it was an enclosed space, and you would not go into that. If something happened and needed maintenance, they would have to stop everything, let the mist settle, and then go in there because, just for safety. Now, quick note, there's something called flash détente that might have some implications in brewing. It's been in America since 2009. There's 13 wineries that have it, and it's when they have to harvest the grapes early because they've got something attacking. For example, in Michigan, botrytis. That's a problem with the vineyards in Michigan. And there's a really good winery who I shall not name. They have great stuff, but they use a flash pasteurizer in a clever way using a flash détente, and they actually get the chromoplasts to explode because after flash pasteurizing, they go into the vacuum chamber, and it just brings out all kinds of other tannins. It makes the aging process of the wines faster. And we already kind of do that when we make our wort. But there's other things that can happen with dry hopping. But right now it's used making wine. Now let's change over to flash pasteurization. Now we're going to talk about Pro Engineering. Wisconsin made, family owned, and they have various tunnel pasteurizers. They make very small ones. The one on the right, I've seen something like that operating at a cidery. The one on the left is doing hundreds of packages a minute. The one that they made for me at my brewery in Pennsylvania, again, was roughly 6 feet, 7 feet working area width by about 40 feet. And that did 100 packages an hour and without a problem. Okay, and what happens is the bottles or cans go through it, and you see in the left picture, you see the sprays. Their sprays are hopefully non-fouling, and they really are, but you still have to inspect them, but you take off the sides pretty easily. And they have little dividers, because as you march through the pasteurizer, you're going to go through different temperature regimes as you gently raise up the temperature until you hit your target temperature. Again, just as I didn't talk through a flash pasteurizer, all the flows, I'm not going to talk through it with a tunnel pasteurizer. But what happens is bottles or cans, in this case, bottles get heated up. Just look on the right. You get a cold bottle, you can kind of see the time stamps. It gets up to its maximum at point G, and then it holds, and then starts cooling down until it exits. So there's heat recovery too. As the package comes in to be pasteurized, ambient water starts warming it up because it's been cooled from a bright beer tank. And that water gets chilled down. Well, that's going to be reused at the back end to help chill down a hot package. So, and here's my product going into the pasteurizer at one of the plants making our things. And there it is coming out. That's bottled, and that's canned product coming out the back end of the pasteurizer. And, you know, in that case, that's one where we can just set the different, we call them basins. Some people call them pockets. You set the temperatures and let them go. And we have a little bottle here, it's in red, with a little computer, a little floating computer that has a little monitor that you stick in the bottle, and you close it off and pass it through. And it just gives a readout at a laptop of what the temperature. So it's a traveling computer. There's various kinds. The one that I love is the Halfman Red Post on the left. There's another really nicely made one in the United States that's cheaper, and it's very fine, very good. Pasteurizers themselves have very good, the more sophisticated ones, such as, well, I'm not going to name brands, but you can actually see the temperatures. They have individual cells. You still verify it with a traveling computer, that way you know you're getting a pasteurization. And by the way, if you look on the one to the left, that one, it was a bottle I ran through, it was 9.5 PUs. Ask me questions if you want to know. You can, using simple microbiology, you can quantify what pasteurization is the minimum pasteurization you need so you can sleep comfortably. And then I can take you through the heuristics of then what do you actually set your temperature for. One of the things I did in my past was I worked for a global brewing group, and I got involved in flash pasteurizer calculations. And I had to use a Monte Carlo model crystal ball built on Excel simply to figure out, we didn't want more than 1 out of every 10,000 cans, and it was cans in this case, to be under pasteurized from target. So what pasteurization did we have to get to assure that we would never have? And the reason why 1 in 10,000 was kind of neat, although it made no sense, is there was, at schools, kids have their little Tetra Pak milk cartons. And the specification was those could have 1 out of every 10,000 can be a leaker with milk. So an executive vice president said, well, that's the standard we got to hit. And that was the standard we hit. Okay, so in closing, good manufacturing practices and attentive cleaning and sanitation of all processes and unit operations in bright beer tank, etc., and in packaging prior to tunnel pasteurization or after flash pasteurization are mission critical to any belt and braces approach to beverage quality, managing the system boundary. You have to look at everything touching the product, including the can, including the end, the lid, including the bottle, including the top. Remember that a lot of threats come in just from the air and just from the package themselves before the product hits it. But you have to look at hygiene, you have to look at hoses, you've got to look at everything. This is what we're all used to hearing. But it's really the system boundary. And again, here's one of our dogs. That's Ira, the black dog. And system boundary around Ira is just like a description of his life. Ira likes to swim. It's summertime. He's spending a lot of time every day. I'm his personal trainer with the other 2 dogs. They go swimming in the swimming pool. But anyway, I have to watch the boundary around Ira, which means I have to keep the chlorine high. I got to make sure I brush him down. I got to make sure he's gone to the bathroom before he goes in the pool. Make sure that he doesn't vomit in the pool. And I deal with that. So anyway, that's the conclusion of my talk. There's my references, and I'm open for any questions.
Very nice, Jaime. Thank you so much. That was quite informative.
Thank you.
I had a question earlier back. The membrane system that you showed a picture of, what size was that? What capacity was that picture that you showed?
Oh, gosh. I'm going to guess that was probably doing 50 hectoliters per hour. But it could have, it's 50 to 100. I didn't ask that question. You can go in that case to Paul, pull down the white papers and ask them for a quote or a size. Their biggest one I think is 500. They have one running 500 hectoliters, 400 and something barrels an hour someplace.
I used to have a Sander Hansen tunnel pasteurizer, 450 cases at a time.
Okay, yeah. Sandra Hans. That was acquired by Crohn's.
Yep.
Crohn's and KHS are kind of like many big organizations. They see another company, they really like it, and they acquire it. And
It
you never
was,
hear the
yeah.
name Sandra Hansen, but the same technology, the chest system, that heat recovery exchange system that you had, you still find it today, except with a Crohn's a label on it.
Yeah, and if you have the footprint floor space, by all means, tunnel pasteurizers are terrific. But I had, instead of the red box, which was, I recall, was about $20,000, the pasteurizer recorder, I found one out of Iceland that was a used for oceanography. It was a little pill about that big, half the size of your little finger, that recorded temperature and pressure, and you would
That
send
sounds
it
like
through.
we have that in Quebec. I can't
Yeah,
remember. Yeah.
it's a little, you put it in a little spider cage and stick it in a can or a bottle and then send it through.
Yeah,
And
it looks like a suppository, and I'm sure since it comes from Iceland, I'm sure someone stuck it up the ass of a whale or something.
all right, I'm done. But yes, but it was terrific. It had software that you would put it into a little box connected to your computer, and it would run out charts of your entire day, and you could see where your pasteurization was done. If you missed any spot, you could go back to that particular run. Since all of the packages were date coded, and the date coder was right downstream of the pasteurizer, it was good quality control for checking to see where everything was pasteurized.
Yeah. One of the questions I'm seeing over here is, at what temperature does there start to be noticeable flavor change? It depends on the product. If you're making a coffee, for example, and you're doing 1,000 PUs, you will not pick up a difference. If you're making a beer, that's a great question, because if you're flash pasteurizing, you want a very high temperature for a very short time. And there's a lot of papers out there that discuss that. I don't want to bias, but conclusions are drawn of a lower temperature, longer time versus higher temperature. With my own work that I did it for a brewing group. We took samples out. At the time, I think the finest flavor panel in the world was in Denmark, the Alfred Jorgensen lab. And this was after Carlsberg had spun them off and before Dan Brew had picked them up. The Alfred Jorgensen, famous yeast scientist, the Alfred Jorgensen lab. And we took samples of 2 of our products from a brewery, and we couried them. I took them to the airport, and we took them before pasteurization and after. And then the next day they were in Denmark, and they chilled them down, and they did testing on them twice a day for several weeks. And there was definitely a difference between pasteurized and non-pasteurized until 3 weeks came. And then statistically, there was no difference. So the conclusion, rightly or wrongly, was beer wants to oxidize. And this was world-class beer made in a modern large plant. But after 3 weeks, the level of oxidation from pasteurized or non-pasteurized, we couldn't perceive it. So for whatever that's worth. Okay, other changes, other questions. I didn't really answer quite what temperatures do you start to be noticeable flavor change. I would say the best way to handle that is, the question might be, what pasteurization unit level? And maybe I'll come back to that. But the lower the PU they can get away with, the more gentle it is on the beer. But I've just kind of told you that, in my opinion, with a lager beer, not talking about IPAs, things happen with hoppier beers. Big things happen with hoppier beers. We're talking about light beers and normal mainstream lagers. Can you talk about the second sensory changes you have found at different PU levels? Okay, any difference between 15 PU flashed versus 15 PU? I have not done 15 or anything of flash versus anything from tunnel like to like. I just haven't had that opportunity. Obviously, the tunnel pasteurizer people will tell you one thing. The flash pasteurizer people will tell you their own thing. The way to decide what is the minimum pasteurization unit is basically get comfortable do a lot of micro or have a lot of micro done, I can recommend labs. And it's not that expensive. There's some really good world-class labs out there. Murio, Silica have labs. I use the ones in the US, but they're also in Canada. They're around the world. And they can give you the aerobic plate counts and several other factors. They can give you anaerobic plate counts and help characterize. And then you just send them samples with different pasteurizations until you're comfortable that, hey, this level, a minimum. And then you basically add another 15 to 20% more on top to protect yourself from under pasteurizing. What are some of the off flavors produced by overpasteurization? Yeah.
Sorry for interrupting. I could add something to that.
Please do, Henry. Yeah.
Because you showed that calculation before.
Yeah.
So I know that quite often, people are talking about plus minus a couple of PUs, and it depends. It makes a huge difference between a flash and a tunnel, of course. But if you look at the calculation, because of the exponent, a few PUs, pluses and minus, won't have a huge impact on the flavor. And as you just said, it's very much beer dependent and very much oxygen dependent. And from my experience, and just generally, I would say maybe if you get to like 70 PUs, then you might realize like a bready flavor, something like that. But it depends so much on the beer style, on the beer itself, and the oxygen content. So that's the big story there. The oxygen content, and this is where you see the differences over time, as you mentioned. Fresh pasteurized beer is pretty much the same as regular beer, but over time, couple of months, then you will be able to tell the difference. That's the story there.
Yeah, that's great. And Henry, do you remember which brewery is the one? I mean, you have several installations where the flash pasteurizer is actually on top of the filler. You know which ones I'm talking about, right? They're in Germany.
There is a few. The Krones does that. KHS does it. You can. There's a couple. I don't want to mention the.
No, it's okay. It's always places that are you can barely. You have to be a skinny worker because they're so tight that it's like you have to be short and skinny, like an Oompa Loompa. But anyway, that's neither here nor there. The next question came up is, what are some off flavors produced by overpasteurization? Well, of course, as Henry said, oxygen content is you got to have less than 25 ppb, or you're definitely going to get cardboard, the vicinal diketones, and you get caramel notes, sweet notes. Does PCR have issues with microbes that produce toxins? I'm not a PCR expert. I've worked with companies that have PCRs. We've done comparative work and found false positives, but this is a few years ago. I mean, I before they were acquired, I was invited by Invisible Sentinel because I was such a cynic of what they were doing, because you're saying, oh, I got nothing, and you say, I got an infected thing over here, but they didn't have the technology, and they have completely changed. But they invited me in to Philadelphia. And it was a great visit. I learned a lot. But again, you'd have to ask, Rheonics, Invisible Sentinel, and Paul, and all the other providers of PCRs, about PCR questions. Next question: if unpasteurized beer lasts, say, 6 months, how much shelf life does pasteurization add? Okay, we're talking about a regular beer and stuff. If it's got less than 25 ppb in it of oxygen, you can give that a 1 year shelf life. I don't recommend that, because beer at 1 year, I mean, I talked to the guys at the Technische here, the head of Heineken. They've drunk the Kool-Aid. We spent millions. We know that our beer is good for a year. Well, between us girls, it's not. You can tell you taste the difference, but it's pretty good. And those of us who've worked with exports or have worked with exports know that a lot of importers kind of hold a gun to your head. They say, you must give us a year shelf life. So you give them a year shelf life and get really upset. But pasteurization will add 50% more to whatever you claim. But if you're making a highly hopped beer, I would advise you to really try to dial down your pasteurization units to something that works for you. It's safe, but you don't want to be clipping the aromatics out, because even if you don't pasteurize, you're going to lose. You're going to convert those hops anyway. Let's see. Do you have a back of the envelope comparison of very good energy conversation? Jim Mellon. Okay. Well, Jim's asking a question about, do you have a back of the envelope compare flash pasteurizer versus a tunnel pasteurizer in terms of energy conservation? Let's just say, because the way a tunnel pasteurizer works, because of spray, and it's shrouded, but you still have more heat losses. You're going to recover 65-70% of the heat, by reusing the zones and pumping around. So a flash pasteurizer, you're going to recover up to 95% of the heat that you put in is recovered. It's kind of like the old-fashioned vacuum deaerators, where you heat it up and vacuum it and you recover the thing. Anything with a plate heat exchanger is going to be a little more efficient, simply because you're not spraying it and losing it to environs of the environment. That's why tunnel pasteurizers have all kinds of panels that shut down to try to keep the convection away from it. But you just naturally are going to lose some. And remember, when you're pasteurizing through a package, whether a can is going to transfer the heat faster than a bottle. A bottle gets a steady state pretty quickly. But you're going to, if you're looking for 140 degrees, you're going to get it a little bit higher in the temperature. The higher you get that temperature of the spray, the more convective losses we're going to have. So I don't want to go into the specifics. There's numbers and the reason why, Jim, is because the numbers I have been determined for me by the vendors who want to sell their equipment. So you always have to put on the detectors there to make sure that the antenna to understand what that really those numbers mean. But a flash pasteurizer will save you more energy. A flash pasteurizer will also use less water because it's not evaporating away, and other reasons. A tunnel pasteurizer, you've got pockets of water, tanks of water. You're eventually going to have to drop those down and empty them. Do a boil out. That drops water. Now, again, when you drop water, if you're in Australia where your water's starved, that could be an issue. But in most of the world, much of the country, the United States, we're blessed. That water is going to go down a wastewater, to a wastewater treatment plant, either the plants or the city's publicly operated plant. They're going to make it potable water and discharge it. And it's not like we're going to go with that water, put it on rocket ships and shoot it into the sun.
But the antibacterial chemicals too, you have to take that into mind.
Yeah, it's true. That's true. But then again, at the publicly operated treatment works, or even your own brewery anaerobic works, they're gonna address some of them. Maybe not all of them. Maybe not the chromates. But I think they're pretty smart with the chemicals they put in about it.
Jamie, if
Let's
you
see
don't
what
mind,
next questions we have.
I would like to ask.
Go ahead.
To add something. I think you made a very valuable point. The vendors' preferences. I think nowadays you can put calculations on one or the other side, favoring flashes or tunnels. They both have their pluses and minuses. And as you said earlier, the filler hygiene might be a potential issue if you flash pasteurize, where a tunnel pasteurizer is more safe. On the other hand, there has been a lot of things done to improve the efficiency of a tunnel pasteurizer. I think it very much depends on the case itself. Yeah. So it's not that easy, and I would not damn one or the other solution. There is reasons for both solutions, to be honest.
Yeah, no, and I sort of hopefully didn't bias this and make it sound like I'm pro Flash. I sleep so much better myself because I'm not worried about, oh yeah, this is my, I don't know if you're going to see it. This is my dog, one of my dogs, but Bailey, Bailey. Anyway. Oh, now she's whimpering. Okay. What I was saying is that you have to have a sterile enclosure over your filler. You've got to have a process to check the air, make sure the laminar flow filters are working, the UV light is working if you have that. I didn't have that. At Trumer Brower Eye in Berkeley, we put up a Crohn's Mechafill tube running 330 bottles a minute. And we had Rheons manufactured the sterile air hood. So we had always positive sterile air. It was just a HEPA filter. We had no UV element. And we used a differential pressure. It was really easy to see that when it got too high, you had to change the filters. And there was like, if a certain amount of operating hours were exceeded, then you change the filters. And that was good for, 2.5 years, something like that. Yeah, we're tunnel pasteurization. You put it in the package and it takes care of everything.
One thing I like to add, for example, if you use cans and you want to package them in cartons, so depending on the filling temperature, you might have to warm them to prevent the sweating.
Yeah.
So it might require a warmer, and a warmer is kind of like half a pasteurizer. So you see the complexity. It's not that simple.
Yeah,
Depends
but
on the whole.
the good thing is a warmer takes up a much smaller footprint.
Right.
Again, your company or Pro make lots of warmers and stuff. And he's talking about makes the packages really nice. Next question came in a flavored malt beverage product. Would you be comfortable removing all chemical preservatives if the product was tunnel pasteurized? It depends on what it is. It really depends on what it is. For example, I make a certain group of products that are Bloody Marys. They're natural Bloody Marys. I have no preservatives in them whatsoever because I have a really aggressive pasteurization regime that is good. And we have our own trigger points. If we see something that gets above a certain level that I mentioned earlier in the thing, at that point, I'll recheck and redo. But there is a maximum number that I would use, and it's something that not every beverage is made perfectly for pasteurization, but those that are, it's great if you feel good about getting rid of preservatives. I feel pretty good about it with our Bloody Marys. Same thing with flash pasteurization. Flash pasteurization can work just as well, but you need a big holding tube and you need higher temperatures for some of the more exotic beverages out there. Next question.
Some juices require a little bit more pasteurization than others as well.
Oh yeah. I made a carbonated juice at the Lion Brewery. My first U.S. brewery that was 100% carbonated fruit juice for a company called After the Fall in Vermont. Thank God we only made one batch, but it needed so much pasteurization units. We had to fill up the pasteurizer, stop it, put a piece of wood at the back, give it time to cook, and then clear it, and then run a little bit more because that stuff needed 950 pasteurization units. So that Meyer, it took us all night to run the stuff, and it was pretty good stuff. It was sickly sweet, and after a few months, it started blowing up cans anyway. Have you seen anyone try to use electromagnetic induction pasteurization? There's several alternatives to pasteurization currently it wasn't my focus to talk about them. One is indeed electromagnetic induction. I don't know anything about it. There's papers out there. One of them is homogenization, like really high pressures, like 40,000 PSI, where you just homogenize it and it comes out, it blows up everything. And in the 60s, gamma irradiation was tried. That did a great job, but it made it affected the taste. It made it very bitter. It made it harsh. And that's just cobalt 60 exposing. Sorry if you guys pick up the dogs. They're barking at FedEx or something. So yeah, there's all kinds of, just like there are with the chemical preservatives, there's ongoing work with alternatives to high pressure pasteurization, super high pressure pasteurization. And I'm not an expert on it. What is the challenge in designing a system for a range of products requiring a range of PUs? That's where you talk to your vendors. Before you accept the dotted line, you have to tell them, I want 0 PUs to go through this, if that's a number. I want 10, I want 20, I want 100, I want 500. And I want line items for how much they would be. For example, with a flash pasteurizer, by design, you can control certain things. But now, I'm not Jeff Gunn's representative, but one way of doing things is if you made a design where the holding tube had additional holding tube elements one could add to hold it at that temperature, possibly insulated, hold it at a longer temperature, longer contract, so that only when you wanted high pasteurization, you went through the more exotic, or you just put in more heat, more steam, more, but you have to specify it. It's just no different. Am I going to do 22-ounce bottles? Remember those? Remember when those were a thing? 22-ounce bottles? You know, so I've talked enough about that. You just have to specify to flash pasteur. That's the same thing for your microfiltration people, because one of the problems you have with sterile filtration is there's a lot of liquids that are going to gel. It's called concentration polarization. That a lot of things are not going to work. Beer will work fine through a sterile filter, but if you're going to do other things too, you might have some challenges because of concentration polarization. That's in cross flow or just by traditional fouling, depth fouling on the thing. Let me see. That's all the questions there. It looks like we have 4 questions in Q&A. What is the challenge? What is the challenge in designing a system to handle range? Oh, okay. That's the question that Bob Pease. It's too bad Bob is not on board right now, because he has no doubt some experience that he can talk about. And I see Ed Michalski has has chimed in. And if Jeff Gunn chimed in, he'd probably say, "Screw you, Jaime." Anyway, I think we've gone through all the questions, everybody, and I think I've taken more time than I'm supposed to.
Excellent, Jaime. Thank you so much.
Yeah, we were here for as long as you want to talk. I could listen to you talk pretty much forever. So as long as
yeah, I stand up and I shout. But yeah, the way to test a pasteurizer really is you go to your vendor. If you're thinking about a tunnel or a flash pasteurizer, and you just go ask them, give me a sample of product. Let me take a sample product from BBT, sample a product that's been pasteurized, either through a flash or taste them, get some, do some independent testing, and make sure you're happy with their product, because what you taste with their product. And again, as we all know, hoppy products are a challenge. But, you know, again, if the consumer is always going to have pasteurized hoppy product, well, you know, they don't know. They don't unless you bring them over to the brewery and say, hey, between us girls, let's taste the BBT. But that's pretty much it.
Excellent.